Good day everyone. Today we're going to solve problems in chapter 8, the open channel. So, a channel is 1.5 meters wide and has a 0.50 meter flow depth. What is the discharge and velocity at n is equals to 0.075 and s is equal to 1 over 150. So, in this example, we have the channel that is 1.5 meters wide. So, the width of the channel B is 1.5 meters. And the flow depth in the channel is given to us, and that is 0.50 meters. So, our flow depth Y is equal to 0.50 meters. So, in the problem, we are told that the slope of the channel is 1 over 150. So every 150 meter, the channel moves in x and it's going to drop by 1 meter. And the roughness of the channel, the Manning's or n value is 0.075, and from these parameters, the question is asking to calculate the velocity of the fluid in the channel and ultimately the discharge. So if we start by thinking about the principle of continuity, we know that the flow rate is equal to area of the fluid times the velocity. So that's a kind of starting point in thinking about these problems, in which in the context of a rectangular channel would be the same thing as saying velocity our velocity is equal to the width times the flow depth. Say your width times the flow depth is going to give you the area. So the problem we have with continuity is we have the area of the channel. So we have the width and we have the depth, right? But we don't have the velocity. And we don't have the flow or our Q. So we've got two unknowns when we try to solve this using the continuity equation. So if we ultimately want to get our Q, we're going to use an equation that is going to relate you to the parameters we've been given and the flow depth, and that equation is Manning's equation. So Manning's equation tells us the velocity in our channel is equal to the hydraulic radius of the channel to the power of 2 over 3 times by the square root of the slope of the channel divided by the Manning's, and which gives us the roughness of the channel. So this is the equation that we can use to solve for the velocity, and then once we've got our velocity, we can solve for our flow. So in this equation, we don't have the value of our hydraulic radius. So the definition of the hydraulic radius for a channel is the channel cross-sectional area divided by the channel's wetted perimeter. So this is the equation. So whenever we do Manning's equation to work out the velocity or the flow, we need to work out the hydraulic radius, which is the area of the flow. So that's the cross-sectional area of the flow. So this is the cross-sectional of the flow. And divided by the wetted perimeter, which is the total length of the side of the channel that is touching water. So it is the total length of the material. So this box right here. So if you wanted to formulate these two parameters, our area is obviously going to be the base of the channel times the width of the channel or the flow depth to give us the cross-sectional area. So A is equals to B times our Y. So now The wetted perimeter is the total length of the size of the channel touching water. So we're gonna have the whole width of the channel. So this part. So in that equation, because the base of the channel is touching water and we're gonna add to the flow depth on this side and the other side because this depth of the channel is touching water. So in this side and this side. So we have gonna add that to 2y. So our wetted perimeter is equal to b plus the 2y. So the total length of the side of the channel that is touching water and giving us resistance is going to be y plus b. So the cross-sectional area is equal to A is equal to B times Y. So substituting the given, so we will have 1.5, which is our B, and the Y, which is 0.50 meters, times the Y, 0.50 meters. So calculating this, we will have a value of 0.75 meter squared of our cross-sectional area. And now let's proceed to our wetted perimeter, which is P is equivalent to B plus 2Y. So our B is 1.5 plus 2 times our Y, which is 0.50 meters. So calculating this in our cycle, we will have a equivalent of 2.5 meters of our wetted perimeter. So now, let's proceed to our getting our velocity. So substitute the result that we get earlier in this equation. So now we have the value of our A and our P. So let's substitute in this equation. So R is equal to A over P. So our A is 0.75 over our P, which is 2.5. So calculating this problem, we will have a hydraulic radius, which is 0.3 meters. So now, since we have everything we need to do the calculation of velocity, so substitute all the givens to the formula. So we will have a velocity is equal to 0.3 to the power of 2/3 times the square root of 1 over 150 over 0.075. Calculating this, we will have a formula. We will have a value of our velocity, which is 0.49 meters per second. So since we have the value of our velocity, we can calculate the flow rate now. So back to the formula of our flow rate, which is Q is equal to area times the velocity. So our A is 0.75 meters squared times our velocity, which is 0.49 meters per second. So calculating this, we will have a value of our flow rate, which is 0.37 meter cube per seconds. So this is our flow rate and this is our velocity. So that's all.